I'm going to continue discussing transformations using the function square root of x. I think it's a nice function to use because it doesn't have any inherent symmetry in it. And so many of the transformations are more clear using this function as opposed to a function that has symmetry, and when you reflect it, the symmetry seems to not change anything. So I'm going to go with one that has no symmetry, and then it applies, everything else still applies to the other functions, even ones with symmetry. It's just not as obvious to see it, so I'm going to go with this function. So the square root of x is important. I have the graph here, just a quick sketch of it. 0, 0, 1, 1, and 4, 2 are the 3 points that I have designated on the graph there. And so discuss the 3 different types of transformations, the vertical, the horizontal, and the other. I'm not going to worry too much about the other, so we're talking mostly about the vertical and the horizontal transformations. First thing I want to do is I want to transform the function using a vertical shift. We're just going to go through these one at a time so you can see what happens. So the first one here, let's try a vertical shift. And a vertical shift may be a vertical shift of 2. All right, so that would be the original function plus 2 is what we're really looking at. Okay, so that would be the square root of x plus 2. Remember that vertical shifts occur outside of the functions where you add or subtract outside. And so basically you take the outputs from the original function and you add 2 to them. All right, so instead of 0, 0, you'd have 0, 2, right? That goes up 2 units. Instead of 1, 1, you'd have 1, 3, right? It's 1 plus the 2. And instead of 4, 2 would be 4, 4, right? You add 2 to that output. About there. And so what you have is basically the same shape, just shifted up 2 units. Every point gets a 2 added to it, and you end up with a new function or a new graph that is, again, the same shape, but just shifted up 2 units. Okay? Every point shifted up. So this is a vertical shift up 2 units. Okay. We can do something similar with subtraction, right? If I had square root of x minus 3, for instance, then you would just start here at negative. You come down to negative 3, and then you go up from there. So again, it would just be a shift of that entire graph down 3 units. Okay. Now let's look at multiplying. So I said that if you multiply on the outside of a function, then you end up either stretching the function or compressing it, depending upon the value of that multiplier. So, for instance, let's take an example like 2 times f of x, right? 2 times f of x. So what we're doing is we're multiplying the function by 2. Every output gets multiplied by 2. So that would be 2 times the square root of x. Okay. All right, so using that relationship, then basically you take each of the outputs and multiply by 2 and you get a point. So in our case, you would take 0, 0, multiply the output 0 by 2, and you get 0 still, right? So that one didn't actually move, didn't go anywhere. Take 1, 1. You take the output, which is 1, multiply it by 2, you get 2, right? 1 times 2 is 2. So the first point didn't move, the second point doubled its distance away from the x-axis. Instead of being 1 unit away, it's now 2 units away. The point at 4, 2, you take the output of 2, multiply it by 2, and you get 4. So 4, 4 would be on the graph. And that one's up here. And I'm going to go ahead and get rid of this prior red graph here just to free up some space. And what you end up with is a graph that is now much taller, right? It's kind of going up faster, all right? And so what we've done is we've stretched the points away from the x-axis. Every point's distance from the x-axis is now doubled. That's what multiplying by 2 will do. So multiplying by 2 is a vertical stretch by a factor of 2, okay? A stretch by a factor of 2. In fact, any time that you multiply by a number greater than 1, it's going to stretch the graph out. Okay, so we have a sort of a general formula for this, or format. We would say that the vertical shift, maybe I'll throw this in red, the vertical shift would be like taking f of x and adding, we call it k. K is sort of our vertical motion there. With the horizontal, or I'm sorry, with the vertical stretching, we would say this is like multiplying it by a, so it'd be like a times f of x, where the a value in this case, a is greater than 1. Okay, that gives you your stretching. Okay, now let's take a look at a situation where we are no longer stretching the graph, but compressing it. And compression is going to be the case where you multiply by something less than 1, and it's going to bring everything down toward the x-axis. Okay, so an example of that, use a different color. An example of that might be, 1/4 f of x. So you multiply the original function by 1/4. Okay, so that would be like, so 1/4 times the square root of x. So you take the original function, all of its outputs, and multiply by 1/4. Now you could use any fraction there that's, or any number that's less than 1. Doesn't even have to be a fraction. You could use decimal. That's fine. But it has to be between 0 and 1 to make this compress. Okay. So by multiplying by 1/4, what you do then is you take each output, multiply by 1/4. So the output of 0, multiply by 1/4, you still get 0. Take the output of 1, you multiply by 1/4, you get 0.25 or a quarter. Take 2, right? You multiply that by 1/4 and you get a half. So you'd be up 1/2 of a unit. So it's 1/4 of the original height off the x-axis. And so the resulting graph is basically really smushed. It's, oh man, I can't even draw that because it's so flat. I can't draw that very well with an arc. It's showing up kind of linear. Well, it's close enough. You get the idea. It really compresses it or flattens it out. Okay, and so that's what we call a vertical compression. This would be a vertical compression by a factor of 1/4. And again, it's similar to the stretching. It's a times f of x, where this time the a value is between 0 and 1. Okay, so you're multiplying by a number less than 1, essentially. Okay, so that gives you 3 different types of transformations vertically. You have your shifting up and down, your stretching, and your compressing. There's one other type of vertical transformation that's called a reflection. So let's take a look at what that one will do. And I'll use another color. We'll go back to blue for this one. Okay, so on this one, to get a reflection, I said that you have to multiply the outputs by a negative number. Okay, so we'll keep it simple. We'll do a negative f of x. So that would be like the negative square root of x. Again, every output gets multiplied by a negative, or turned negative in this case, because they all start positive. But if they started negative, you would multiply by negative to turn them positive, so it would be the opposite. Here, start with 0. 0 multiplied by a negative is still 0, so that one doesn't change. Positive 1 output, multiply it by a negative 1, becomes negative 1. Positive 2 output becomes a negative 2. And you end up with a graph that, instead of going up to the right, it ends up going down to the right. Okay, the dashed graph is the negative square root of x. And this is a reflection of the original graph across the x-axis, or a vertical reflection. Okay, so reflection across x-axis. That's what occurs when you multiply the outside of the function by a negative. All right, and so anytime you have a times f of x, where a is less than 0, you end up with a vertical reflection like this across the x-axis. Now, if a is not negative 1, if it's like negative 2 or negative 1/4, then you end up with a combination of both a reflection and a stretch or compress. Okay, so if it was negative 2, it would reflect and stretch. If it was negative 1/4, it would reflect and compress. Okay, so you can combine these things. You can even combine both the vertical shifts with the vertical compression, reflections, compression stuff. And you could put them all really into the same graph, or into the same function. So for instance, if you wanted to do negative 2 square root of x plus 1, okay, this would be an example of a combination of multiple transformations. And so in that case, and these are all vertical transformations. And so in this case, what you would do is you would apply the transformation that's closest to the graph, or closest to the original function, and then kind of work your way out, using order of operations essentially. And so this negative 2 that's multiplying the root will both reflect and stretch the graph out. So you take the outputs and multiply by a negative 2. Okay, so 0 will stay 0. 1 will become negative 2, so it's reflected and stretched away from the x-axis. 2 will become negative 4, which I did not draw on my graph, and I should have drawn that farther down to do this. Okay, good enough. Okay, so there's roughly negative 4, 4 comma negative 4. And so you have this graph that kind of goes down. However, I'm not done yet because I've only applied the negative 2. Then I yet have to shift those points up 1. So instead of being at 0, negative 2, and negative 4, I need to then add 1 to those. So it would actually be at 1, it would be at negative 1, and it would be at negative 3. Okay? And so that gives us the actual final graph after all of the transformations have been performed. I can connect the dots. Okay, and that would give me all of the outputs. Okay, all the proper outputs at positive 1, negative 1, and negative 3. All right. So again, performing operations outside of the function will change the graph in a vertical sense, either by shifting or by stretching, compressing, or reflecting, depending upon the value of the number and the operation. In the next video, we'll do some horizontal work.